In the previous class we were discussing about the Bernoulli's equation in its steady and unsteady form. Now we will try to solve a problem which is an elusively simple problem and a problem which nowadays is even dealt with in school level, but we will try to see what kind of complication it is there as a part of solution of the problem and to what extent people tend to oversimplify this problem. So, the problem is about a tank emptying problem. There is a tank maybe cylindrical, but it could be of any shape. There is a free surface of the fluid, say water as an example, and there is a small hole with area A2 which is much larger than much smaller than A1. Question is, how much time will it require from an initial height to make this tank empty? That is the question, and you can assume inviscid flow for your analysis, although in reality the flow is not inviscid, but it is not a bad assumption so far as this kind of practical problem is concerned. So, clearly because the front is coming down as the fluid is getting out of this tank, the flow is unsteady, and even if all other assumptions of Bernoulli's equation are satisfied, the unsteady assumption may be questioned. So, it is better to keep the unsteady term and see what are the situations when the unsteady term may be considered or may not be considered. So, we will consider the unsteady version of the Bernoulli's equation. By considering a streamline. So, I am just drawing some representative streamlines. So, representative streamlines are like this, and let us say that we consider 2 points 1 and 2 located on a streamline, where 1 is at the area A1 and 2 is located on the area A2. First of all, the velocities at the sections 1 and 2, when we are assuming inviscid flow, we are implicitly assuming that the velocities are uniform, because viscous flow will give rise to a velocity gradient. So, when we say the velocities are uniform over 1 and 2, we can write this. So, the question is that we have earlier discussed that again this equation is also a very elusive equation, because when we write this not only rho is constant, but also we are assuming that this V1 is the velocity at point 1 here, but fundamentally this equation is A1 into V1 average is equal to A2 into V2 average. That means A1 into average velocity over the section 1, not velocity at point 1, but velocity at this identified point 1 and the average velocity over the section 1, they are the same when the flow is uniform over the section, and that is what is the assumption behind this equation when 1 and 2 are meant to be points 1 and 2. Then the next point, so clearly this is an unsteady flow, but A1 V1 equal to A2 V2, right. So here if you recall the derivation of this, there was a continuity equation which was integrated. In that equation this term was set to 0. There could be various logics for which this term could be set to 0. One is steady flow, clear, steady flow but rho may be variable. The other case is a clearer case where rho is a constant, it may be unsteady flow, because although rho is constant but velocity may be varying with time, that makes it an unsteady flow. So this is such an example, rho constant but unsteady flow. So when you have rho constant but unsteady flow, you have A1 V1 is equal to A2 V2. Then let us write the unsteady Bernoulli's equation, which is more important. So so in addition to the normal terms, the additional term is because of the unsteadiness. Now a big concern for this problem is how do you calculate this. So to do that, what we will do is, see, we will consider that this integral is over a streamline starting from 1 to 2. By the way, the height of this h is a function of time. Initially it may be h naught and then this h is a function of time. So then this one, this velocity is velocity where? This is the velocity which is a variable between points 1 and 2. Out of this, the major part of the streamline is within the region over which this area is large. Only a minor part over which the streamline bends is close to the area A2. So primarily we can say that this is approximately equal to okay. This is an assumption that the primary contributor to this integral is the velocity within this large tank. So, this is equal to minus h, and therefore, now let us come to the equation. So, P2 and P1 both are P atmosphere. So, this term is 0, Z2 minus Z1 is minus h, and V2 is A1 by A2 into V1. So, we can write A1 square by A2 square minus 1 where yes by 2, where V1 is dH dt. So, you can clearly see that it is a non-linear differential equation in H, not easy to solve at all. A simplified scenario is that when this unsteady term is much less than the other terms. So, a simplified scenario V1 may not be small, but still this is 0. So, this is negligible, and the other is so then in this case right from this equation, and because A2 is much less than A1, this term can be neglected. So, then this equation is left with V2 square by 2 minus GH is equal to 0. So, V2 is approximately equal to root 2 GH. This is the so called Torricelli's equation. So, this is an example where a problem which is traditionally solved by using this as a formula may lead to a condition when this formula itself is not justified, and then we have to go through this complex exercise of solving this equation. You can pose this or throw this as a challenge problem to the students of your class, and then ask them to assess that in the full form if this equation is solved, then how the solution deviates from the solution from the Torricelli's equation. What are the ranges of non-dimensional parameters over which that these two agree, and what are the ranges over which these two do not agree. That gives a complete understanding to the dynamics of this problem. The final agenda in this particular chapter is to discuss Euler equation in streamwise and cross streamwise coordinate. So, the whole objective is that instead of using x, y as a generic coordinate system, we will shift the coordinate system to a streamline and a line, another line which is normal to the streamline. The objective behind this is that because the flow is always having a velocity which is tangent to the streamline, therefore, with respect to the streamline coordinate, it is a pseudo one dimensional problem. So, it reduces the dimensionality of the problem, that makes the streamline convenient, a streamline coordinate such a convenient coordinate to use. So, let us say that this is a streamline and this is a fluid element which is coaxial with the streamline, which is a cylindrical fluid element. So, a curved cylinder as an example. Now, we will identify all the forces on this, assuming the flow to be inviscid. So, this is P. Let us say that this distance is delta S, and let us assume that the difference in vertical elevation between these 2 points is delta Z. These 2 points are the centers of the 2 sections and this angle is theta, which is angle between the horizontal and the axis of the cylinder. So, this is P into A is the force and this times the A into the is the force. So, we can write resultant force along S is equal to the mass of the fluid element times the acceleration along S. So, resultant force along S, one is these 2 forces plus there is a gravity force delta m into g, and a component of that along the negative x direction, negative s direction will be minus delta m g sin theta. So, P into A as I told you that with respect to the streamline coordinate it is a one dimensional type of flow. So, V is a function of T and S, okay. Into delta m, sorry, into A into delta S, right, rho into A into delta S, right. So, if we now write sin theta it is this one. So, this terms, let us see which terms get cancelled, these terms get cancelled. You can also cancel A into delta S from both sides and take the limit as delta S tends to 0. This is AS. So, this is the Euler's equation in the streamwise coordinate. Surprisingly, although the velocity is along the streamline, the Euler's equation in the cross streamwise direction will also be relevant, because although the velocity is along the streamline, there is an acceleration which is normal to the streamline, and this is because of the curvature of the streamline. So, this is the S component of the equation. If you consider a coordinate n which is perpendicular to S, so what is An? An is minus V square by R, where R is the local radius of curvature of the streamline. So, this is like the centripetal acceleration because of curvature of the streamline. So, this acceleration is not expressed in this way, it is a sole effect of the curvature of streamline and not due to physical change of the velocity with respect to position or time. Okay. So, to summarize, in this particular chapter what we have studied the dynamics of inviscid flows. So, in dynamics of inviscid flows we have started with deriving the Euler's equation of motion, first Cartesian coordinate and then streamwise and cross streamwise coordinate. Then streamwise and cross streamwise coordinate was the last thing that we did, but in between we also derived a vector form. From the vector form we eventually derived a scalar form, and the scalar form under certain special circumstances led to the Bernoulli's equation, which we analyzed for steady and unsteady flow. And the final thing that we did was to express these equations in streamline and streamwise and cross streamwise coordinate instead of the traditional Cartesian coordinate. So, we have studied so far up to this, but to move further forward we have to understand that so far somehow we have tried to get rid of writing the equations from an Eulerian or control volume perspective. We have considered a control mass or a fluid element and tried to express the equation for the fluid element. Eventually in fluid mechanics the whole art is to transfer these control mass based equations to control volume based equations, and that needs to be done because all the parameters in fluid flow equations are essentially control volume based parameters. So, there requires a transformation that transfers the control mass based equation to control volume based equation, or a systems approach to a control volume based approach. This is required more so because the systems approach is an approach based on which the traditional Newtonian mechanics and equations of Newtonian mechanics has been established, but the control volume approach is the approach that we follow for fluid flow analysis. So, there requires to be a transformation that transforms one approach to the other, and that is achieved by a very well known theorem known as Reynolds transport theorem. So, we will study that in the next lecture. Thank you very much.